Today we will share with you on a video for Form 5 Chapter 1 of Chemistry, the rate of reaction. Before we go further into the topic, it is good to understand what we need to know overall in the whole topic. So for rate of reaction, we need to know about the definition and followed by the calculations involved in the chapter. After we understand the calculation and the definition, we will then move forward to the factors affecting the rate of reactions, and there are altogether 5 factors. And the last part will be the collision theory for rate of reaction and also the energy profile diagram associated with the collision theory. First thing first, we will go into the definition. So for this particular video, I would like to share with you on the definition and also on the calculation involved. For the definition of rate of reaction, we usually represent it with a chemical equation. For example, we have a simple chemical equation A plus B to give C plus D, in which A plus B are the reactants involved and the C plus B will be the products obtained. So throughout the time, the reactants will be used up to produce the product, and hence the amount of reactants will be slowly decreasing while the amount of the products will be slowly increasing. So this will be the formula for the rate of reaction, in which rate of reaction equals to the amount of reactant used up over time, or rate of reaction equals to the amount of products obtained over time. So from these two equations, from these two formulas, we can see that it doesn't matter if we measure the rate of reaction by focusing on the reactants or by focusing on the products. And from here, what we need to understand further is how to represent it with a graph. For the rate of reaction involving reactants, the x-axis will always be time. The time can be either seconds or minutes, and the y-axis will always be the amount of reactant used up. So the amount will always be represented by concentration. For example, in this particular condition, the reactants will be either A or B, So this is a concentration of A changes with time, or the concentration of B changes with time. Both can be represented by the same graph because both are the reactants. And since the reactants are being used up, that means the concentration of reactant will be decreasing with time. The graph will be like this. The concentration of reactant is decreasing with time. And for the product, if we would like to represent it by a graph, the same goes to the x-axis, which is time. It can be either in seconds or in minutes, and the products obtained will be C and D. We can either study the concentration of C or the concentration of D, and this will be the graph. Because the products will slowly be obtained when the reactant is being used up. So the concentration or the amount of the product will always increase with time. And this is an increasing curvature showing that the concentration of product is increasing with time. After we understand on the curve of the graph whether it represents a reactant or the product, we will then go further on the calculation. So bear in mind that the rate of reaction is always a measurement of amount of reactant used up over time or the amount of product obtained over time. Okay, so we go into a simple understanding on the graph of rate of reaction. For example, we have a curvature of graph in this way. So what we know from here is this is an increasing curvature. That means this one will be a graph of the concentration of product versus time. So students need to know how to interpret the graph in the first place before we continue to the calculation. Once we know that it is a measurement of the concentration of product over time, then we have to understand what is the meaning of the curvature at different time. For example, we give a particular example at t equals to 1, at t1. So at this particular t1, if we bring up to the curve, this will be the point of concern. So according to the formula of rate of reaction, rate equals to amount of product obtained over time, and this is a product over time. So that means the slope equals to the y over x equals to the concentration of product over time, which is equals to the gradient of graph equals to the rate of reaction. That means for a particular graph of concentration of product plotted versus time, the gradient of the graph can be used to represent the rate of reaction. For T1, how to measure the gradient of the graph at T1? Because this is a curvature, and hence students will need to know how to draw a good tangent from the graph. If at this particular T1, the tangent can be drawn in such a way that it must be a line like this, in which it is exactly 90 degrees or directly perpendicular to a line drawn on the point itself. So this is the tangent that we draw based on the graph at this point. And from the tangent of the graph, we can therefore find the gradient of the graph by using the change in the concentration of product over change in the time. And hence the rate of reaction at T1 equals to the change in concentration of product over the change in time. So I will present another time for you to see how to measure the rate of reaction at different time. So let's say we have another example at T2. So from here, student, you need to extrapolate the T2 to touch the curve, in which you can lock up a single point on the curve. After we lock up the single point on the curve, then start to construct a tangent which is perpendicular to the line. This is the one, for example. And from the tangent, we can then measure the change in the product and also the change in the time. So now the rate of reaction equals to the change in the product versus change in the time for T2. The last example I would like to stress here is how if the time falls at this particular region, T3. So we use the same way to extrapolate it to the curve to find a single point. And at this single point, we still construct a tangent, but because the tangent must be directly perpendicular to here, so this will be the tangent line. And from this line, student will know that there will be no change in the product concentration, although there is a change in time. And hence, the rate of reaction at T3 equals to 0. Because it gives us a 0 gradient. So back to this point, when we say the gradient of the graph equals to rate of reaction, hence from different gradient calculation, we will know whether the rate is a large rate of reaction or it is a small rate of reaction. We have 3 particular time here, where we have T1, T2, and T3. And from these 3 particular time, we will be able to find out the gradient of the graph, which represent the rate of reaction. And from the rate of reaction of these 3 particular points, we can see clearly that the rate of reaction at T1 is the largest rate because of the steepest gradient. So a large rate also represents that the reaction proceeds very fast because it is at the beginning of the reaction where a lot of reactants are readily produce the product. When we go to T2, the tangent or the gradient of the graph is no longer steeper comparing to T1. So this one will give you a small rate. And small rate because of a less steep gradient, and this small rate represents the reaction has slowly slowed down. While at T3, the rate of reaction equals to 0 because the gradient is 0, and hence this represents the reaction has stopped. That also means that the reaction is completed. So from here we can see clearly that how are we going to interpret different points at different time when we are given with a curvature of the concentration change of product versus time. And this particular technique is applicable to reactants as well. So I will now share with you a particular calculation on the rate of reaction. Calculation on rate of reaction is typically following a reaction condition. For example, in this particular example, we have a chemical reaction involving a reactive metal and acid. So when the hydrochloric acid is reacting with magnesium, magnesium chloride is formed as product, and also the hydrogen gas. So from the reactants and the products, the volume of hydrogen gas evolved is studied with the increasing of time. And here is the plot of volume of hydrogen gas evolved with time. So this curvature is in an increasing form, showing that the volume of hydrogen gas is slowly increasing with time. So for this particular calculation of for the calculation involving in the rate of reaction, usually it will be the average rate or the instantaneous rate. And what is the difference between them? We start with the first one, the average rate of reaction. When we see the word average, that means the average can always be calculated by a total divided by a total. What it means? So what it means? It means that if we are calculating average rate of reaction, and since the rate is the amount of product versus time, hence the average rate of reaction will be the total amount of product versus the total time. So for the A, to calculate the average rate of reaction, it can be equal to the total volume of hydrogen gas versus total time. So according to the time scale over here, where is the total time and what is the total of volume of hydrogen gas? We can see that the graph is slowly increasing, showing that the volume of hydrogen gas is increasing with time. And when the graph is slowly increasing up to a certain stage, that at this point, the graph slowly increase up to this point and it start to level off without any change. So the graph can be represented by this point where we say average rate of reaction means the total of volume of hydrogen gas versus total time, and we are talking about the whole reaction. That means when the reaction has reached completion, has reached 100% completion. So the total volume of hydrogen gas will be, for example, 39 centimeter cube divided by the total time when the reaction has reached completion, which is around 3.4 minutes. And hence we will be able to obtain our answer, and please remember to always put the correct unit. Now we go on to the second question, in which we are asked to calculate the instantaneous rate of reaction at time equals to 3 minutes. So 3 minutes is not a good way to represent. We will change it to the 2 minutes, for example. So the instantaneous rate of reaction at time equals to 2 minutes, that means it is here. What is the meaning of instantaneous? Instantaneous rate of reaction. From the word instantaneous, we will see instant. That means it is the rate of reaction at one particular time at t equals to 2 minutes. This is at one particular time, and if we need a particular time, so for instantaneous, we always need to draw a tangent and find the gradient at particular time. So when we are looking for instantaneous rate of reaction at time equals to 2 minutes, then we will have to extrapolate the graph at 2 minutes up to the curve to find a fixed point. This is the point where we are conducting our tangent. So as what we have shared just now, the tangent can be something like this, and we can then find out the change in the volume of hydrogen gas versus the change in the time. So now, let's say the change in volume of hydrogen gas will be 45 minus 22 versus change in time can be 3 minus 0.8 minute, and hence we will have 23 centimeter cube divided by 2.2 minute. So you will then find out the instantaneous rate of reaction at time equals to 2 minutes. Soon we go to C, in which we are asked to find the average rate of reaction in the first 2 minutes. When we are required to find out the average rate of reaction in the first 2 minutes, so what is a key point here is we are asked to find the average rate, not instantaneous rate, and hence no gradient is required. We only need to use a total of amount divided by total time. But the condition is fixed in the first 2 minutes. That means we do not need to concern about the rate of reaction after 2 minutes. We only need to concern about the rate of reaction in the first 2 minutes. In first 2 minutes equals to, since we need to know the total of volume of hydrogen gas in the first 2 minutes divided by the total time, that is the first 2 minutes. From the graph, we can easily obtain the volume of hydrogen gas in the first 2 minutes. That is 35 centimeter cube divided by the first 2 minutes, that is 2 minutes. And hence we will be able to obtain the answer and remember the correct unit. And for the last point, where we are required to find out the average rate of reaction, and now the condition is set to the third minute. Third minute, that means this is the third minute. According to the time scale, we are not concerning on any other minutes. We only need to know the average rate of reaction in the third minute. That means we do not need to know about the first minute or the second minute, but we only need to know here, that is in the third minute. So the same goes to the application of average rate of reaction in the third minute equals to total of volume of hydrogen in third minute divided by total time, third minute. So from here, we will use the volume of hydrogen in the third minute minus the volume of hydrogen in the second minute divided by total time, which is third minute. So from the graph, in third minute we obtain 39 centimeter cube, minus out the volume at the second minute, which is 35 centimeter cube, and the total time will be 3 minus 2. And student, from here it is very obvious that the average rate in the third minute will be 4/1. Minute equals to 4 centimeter cube per minute. So with that, we have covered different calculations involved in particular in this chapter. In particular, the average rate of reaction, and this means that when the reaction has reached completion. and the second one will be the instantaneous rate of reaction. And usually when we see this word, that means it is at one particular time. For example, at time equals to 2 minutes. And also different types of average rate of reaction. Average rate of reaction in the first 2 minutes, that means we do not need to know about the rest of the minutes. And also the average rate of reaction in the third minute, that means we do not need to know about the minutes before it and also the minutes after. So here is the conclusion. Before we end this session, for rate of reaction and introduction, students need to know about the definition, that is, the rate of reaction equals to the amount of reactant used up versus time, or the amount of products obtained over time. And because of the reactants is always decreasing, so the graph will be in a decreasing order, and the products is always in an increasing order, so the graph will be increasing as well. Follow up from here, students need to understand well on how to interpret a graph to calculate the rate of reaction. So usually the graph can be interpreted in different ways, and because the rate of reaction means the rate of reaction is defined as the change of the amount of the product versus time, or the amount of reactant versus time, and hence the gradient of the graph will be the calculation for rate of reaction. So at different particular time, it brings different rate of reaction, and hence a different meaning on how fast or how slow is a reaction proceed. So I also share with you on a particular calculation on a rate of reaction, in which usually the rate of reaction will be on the average rate or the instantaneous rate at different time. And if the average rate, we have to know whether it is average rate of reaction throughout all the time, or the average rate of reaction in the first few minutes, or average rate of reaction in one particular minute. Okay, so that's all. Thank you.